I hope I'm audible. Yeah.
Yeah,
Let me share my screen. Right. Yeah. So is it visible?
yeah, it is.
Sorry. Yeah. One sec. Yeah. I think it is visible, right?
Yeah, it is visible, but you can go to
Yeah.
full mode.
Yeah. Full mode. Yes.
Yeah.
Yeah. Once again, thank you for introducing me. So as Govind introduced, today I will be speaking on the observation of kinetic Alfvén waves inside an ICME magnetic cloud, which we have observed at 1 a.m. So let us begin. And I hope I won't be boring you all for the next 30 or 40 minutes. Let us start with something with which we all are familiarized, that is the coronal mass ejections or CMEs. Basically, we know that the coronal mass ejections are large-scale eruptions occurring on the surface of the sun, through which large amount of magnetized plasma is expelled into the interplanetary space, where it then expands and then propagates to the heliospheric. So we know that there is a interplanetary counterpart of the coronal mass ejection, which is called as the interplanetary coronal mass ejection, or ICME in short. This ICME is basically a three-parter structure consisting of a leading shock front, which is followed by turbulent sheath region, which exhibits signatures such as high temperature and high compression. And behind this turbulent sheath region, we have the magnetic cloud, which is an ordered magnetic structure, which sometimes has a magnetic flux rope, or we can say a magnetic rope-like structure embedded inside it, which has its foot points anchored at the sun. And along with the co-rotating interaction region, the ICMEs, or in short CR, the ICMEs are basically considered as one of the major drivers for the space weather, and thus they have been point of research for many decades. So we know that whenever an ICME propagates into an interplanetary space, this ICME encounters various structures which magnetic structures basically affect directly or indirectly the ICME dynamics. In the sense, sometimes during the propagation, the ICME may interact with the previously expelled CME, causing something called as CME-CME interaction, or it may sometimes even interact with the high-speed streamer, causing a CME-HSS interaction, or sometimes it may even interact with the CIR, causing CME-CIR interaction. Or in few cases, it may even interact with the surrounding solar wind. These interactions has profound implications on the overall cloud dynamic or ICME dynamics in such a way that it affects the structure of the ICME, or sometimes it even modifies the thermodynamic behavior of the ICME by changing the polytropic behavior of the ICME, or even it sometimes accelerates or decelerates the CME, and sometimes it even causes rise in the temperature anisotropy of the ICMs, which may in some cases generate some kind of kinetic scale fluctuations or instabilities of waves. Along with this, these interactions also affect the intrinsic dynamics of the ICME flux. Uh, Usually because of this interaction, the ICME flux route may get disrupted in such a manner that it may sometimes get eroded, or it may sometimes uh, basically it can pancake, or sometimes it even twists, or basically it can lead to formation of internal current sheets inside the ICMs. This processes basically sometimes can cause the ICME flux rope to basically fragment into large scale plasmoids. And along with this, there have been several observations and numerical theories which suggest that these interactions may even sometimes lead to the generation of some MHD scale waves, or basically some plasma waves. One of the most observed one is the uh, observed one, or the most interesting one is the Alfvén waves. The Alfvén waves are basically the most fundamental forms of MHD waves, which are oscillating at low frequencies, and they are ubiquitous in nature, implying that they are observed in various astrophysical plasmas and laboratory scale plasmas. And they are basically transverse oscillations, which are propagating along the magnetic field lines with the magnetic tension acting as a restoring force. And they have been observed in various environments such as solar wind, planetary magnetosphere, neutron stars, and so on. And similarly, there have been recent observations of Alfvén waves in ICMEs. In the sense, they have been recently observed by small scale in the small scale flux ropes, and recently by our group, we have made observations in the shock sheath region, or even within the ICME HCS interaction region, or a type of the Alfvén wave, that is the torsional Alfvén wave and the surface Alfvén waves, have been identified in the ICME flux mode. However, these waves are kind of an MHD modes. There is another kind branch of waves which is called as the kinetic waves, which have not been that explored in the context of ICMEs. So one question arises: what are exactly these kinetic waves, and why should we even study these kinetic waves? We know that our Alfvén waves are basically an MHD waves, or the MHD works on the MHD theory, which basically treats the plasma particles as a fluid. In the sense, we are neglecting the individual behavior of the particles, and we are mostly we're treating them as a collective behavior, collective thing. So because of which we are uh, just observing large scale phenomena. However, whenever we go to the kinetic theory, the kinetic theory treats these particular plasma particles as individual particles, thus enabling us to study their individual behavior, such as, for example, we can study the wave particle interactions. And thus, this kinetic domain is very much interesting to study. So, we know whenever we have a wave, usually the wave carries the energy through the system, and whenever we have plasma wave, this wave basically transfers its energy through a process called as cascading. This cascading occurs from large scale to the smaller scales, where as it cascades to the smaller scale, it reaches a particular scale where it basically dissipates the energy in the form of heat to the surrounding plasma. So now, when the wave scale approaches the kinetic scale, by kinetic scale, what I mean is basically as the wave cascades, it reaches the scale length which is equal to the ion gyro radius or ion gyro frequency. At this particular scale, we say that our wave or a plasma wave has made a transition from MHD scale to the kinetic scale. And whenever this happens, so what exactly happens is uh, basically the ion motion starts to decouple with the electron motion, causing the pronounced electric and magnetic field in the parallel direction, which basically causes the uh, uh, plasma particles to interact, or the wave directly, I would say the wave to interact with the plasma particles uh, via processes such as Landau damping, or you would say cyclotron resonance, cyclotron damping, or sometimes transit time interactions, causing the wave particles uh, causing the wave and particle to interact, which in general causes the net heating and cooling of the plasma. Thus, it makes very interesting to study this kinetic branch of the waves. And so now one question might arise: have there been any observations of this kinetic? So, or let us see a few things before that, and then we'll come to that thing. Okay. Basically, we know that our idea, Alfvén waves. Alfvén waves are basically ideal MHD waves, and usually they do not transfer any energy to the surrounding plasma particles. However, once their wave scale makes a transition to the kinetic domain, they makes a transition to two branches of waves. First one is the ion cyclotron waves, or I would say alpha ion cyclotron waves, which are basically left-handedly polarized waves, which are propagating in a direction parallel to the magnetic field. These waves are usually formed whenever the wave vector condition, that is k parallel, is far greater than the k perpendicular at whenever k perpendicular dot rho I is equal to 1, which basically uh, is your kinetic domain, where your k perpendicular and k parallel represents the perpendicular and parallel components of the wave vector, and rho I is the ion gyro radius. So these ion cyclotron waves are what I would say, there is another extension to this wave, which we call as an alpha ion cyclotron wave, which is nothing but a wave which comprises of the both low frequency alpha wave along with that high frequency ion cyclotron wave. This alpha ion cyclotron wave, or AIC wave, which I'll be discussing in few slides, basically interact with the surrounding plasma via process such as cyclotron damping, and thus they dissipate the energy in the form of heat. And there is another branch of the kinetic waves of the Alfvén, which are basically the kinetic Alfvén waves, which are right-handedly circularly polarized waves, which move in a direction perpendicular to the magnetic field. And they are usually formed whenever the K perpendicular is far greater than the K parallel at gyrokinetic conditions. And usually it is observed that the KAWs are far compressive than the AIC waves. And They also support process such as stochastic heating, which basically is applicable only to large amplitude waves. So along with this, there are few other waves which I have categorized depending upon the direction of propagation. That is the parallel ones which we have already discussed. That is the ion cyclotron wave, and along with there is the Whistler wave. By parallel, in the sense I mean the propagation angle for the wave is roughly around 0 to 40 to 45 degrees. Uh, and anti-parallel, which is basically between 135 to like 180 degrees. So there is another branch of waves which we call as the Whistler waves. The Whistler waves are basically high frequency electromagnetic waves, uh, which basically are right-handedly polarized, and they are moving in direction parallel to the magnetic field. And just like the your AIC waves or ion cyclotron waves, they interact with the matter with a process called as cyclotron resonance. And the another branch is basically of perpendicular KAW waves, which we will be discussing throughout this talk. And the last branch is basically the obliquely propagating waves, in the sense the wave which propagates with an angle of 45 to 75 degrees. This particular branch of waves have two different waves. First one is the oblique KAW waves, which are nothing but your KAW waves which interact which are again basically they are interact with the process called as transit time damping. And unlike the KW, which were having right-handed polarization, in this case they are having mixed polarization. And another wave is basically the mirror mode waves. The mirror mode waves are quasi-static waves which are formed between pressure anisotropies, and or sometimes due to some instabilities. They again interact just like your KW with transit time damping, and they are this similar to oblique KWs. They have mixed polarization. So now what I was saying earlier, that are is this kinetic wave possible in ICMEs, in the sense can we observe this kinetic scale waves in ICMEs. So recently there have been few studies. First one was conducted, or I would say the one was conducted by the Alates group, where they observed the alpha and ion cyclotron waves, AIC waves, within the ICME sheath region. This AIC waves, as per their conclusions, was basically mostly found near the start point, or I would say near the shock front, and which later on diminished as we move away from the shock front and reach the leading edge of the magnetic cloud. And recently, our group has also observed this unique branch of the kinetic wave in the ICME Magnetic Cloud. And we were successfully able to establish the link between the fluid and kinetic scale in a low beta plasma environment, such as an ICME Magnetic Cloud. Apart from this, there was one study conducted by Zhao et al., where they were performing multi-spacecraft observations using solar orbiter and wind, where they observed the presence of KW waves inside a ICME-driven shock. Still, the question arises, can we observe the kinetic Alfvén waves in magnetic clouds? In the sense, we observe, it is true that we observed AIC waves, but can we observe the second branch of the kinetic waves in ICME magnetic clouds? So before we address this question, let us see where these KW waves are basically observed, like what are their implications on the surrounding space plasma environments, and what are the different generation mechanisms, and then we'll come to this. So in literature, there have been several observations of the KWs. Few of them are basically, they are observed in solar wind turbulence. They have been observed in auroral electromagnetic turbulence. They have even observed between the magnetopause and boundary layer. And they have been even observed with the magnetohydrodynamic plasma sheet near the onset of the substorms. And recent observations as well as numerical studies suggest that this KW's waves can even be generated at the near the reconnection exhaust formed because of the magnetic reconnection in the current sheets. Particularly, there is one observation or a study conducted by Gershman et al., where they used the data from the MMS spacecraft to observe the KW waves in the magnetosphere, where they were able to basically identify the conservation or identify or basically demonstrate the conservative energy exchange between particles and plasma field. Now, let us see what are the implications or what are the effects caused by the KW in different environments. Usually, the scale length of the KW waves is far greater than the electrostatic waves, because of which they support a process of anomalous transport, where they cause diffusion of the radioactive particles and thus support the and thus cause the ring currents. And along with that, basically they hit the electrons in the mag, uh, magnetopause, and basically because of which causes generation of stable auroral arcs. Also, some studies suggest that they can even cause viscous interaction between the solar wind and magnetosphere. They can even lead to some turbulent heating in the solar wind and magnetosphere. And furthermore, they have been even observed in the course of the fusion plasmas, where observations suggest that they transport energy away from the core and deposit at the edge of the reactor. So this suggests that this basically tells us how important your KAW waves are, are there are or how important the presence of KAW waves is there in the context of various astrophysical as well as laboratory scale plasmas. So now let us see the different generation mechanisms. First one is basically the mode convergence. Second one is the phase mixing, velocity shear. Then there is toroidal coupling, or sometimes even resonant absorption or interaction between the interaction of the Alfvén waves with inhomogeneous background structures, or sometimes they are generated even by the ion beam plasma interaction in uniform plasma boundary, or sometimes they are even generated by some instabilities. So this particular discussion tells us that there are multiple ways through which this KAW waves are generated, as well as there are far implications of these waves in different astrophysical plasmas, thus making them very important to study. Furthermore, we know that our ICME Magnetic Cloud, it is a closed structure having low plasma beta conditions, and basically several studies have been conducted in the past to study this microscopic structure of the ICMEs. Along with along with there have been some observations of the MHD scale waves. However, the kinetic domain of the ICME remains unexplored. Thus, by conducting this study, we aim to explore the kinetic domain of the ICMEs. Moreover, we know our group has itself identified one branch of the kinetic wave, that is AIC wave, through which we were able to establish a link between the fluid and kinetic scale. Still, by this study, we wish to establish the link between the fluid and kinetic scale waves in the ICME clouds. Along with that, we wish to study the dissipation of the MHD wave in this MHD Alfvén wave in the kinetic domain. Moreover, we know that whenever there is a kinetic scale wave, there is a wave particle interaction. And whenever there is a wave particle interaction, the energy is exchanged directly from the plasma to the waves. Thus, it is basically, I would say, a microscopic process. And till now, there have been less exploration of the ICME clouds in the microscopic domain. In the sense, if you are able to identify the microscopic process involved in this, involved because of this kinetic scale waves, you will be able to understand the process such as heating and cooling of the ICME plasma, which has been focus of recent studies. For example, one study conducted by Lee et al., where they suggested that the Alfvén waves are hitting the ICME clouds. And this, as I said earlier, usually the Alfvén waves don't directly transfer the energy. They basically go through the cascading to dissipate this energy. Thus, studying these modes of kinetic waves will help us to understand the different processes which are occurring in the kinetic domain of the ICMEs. Thus, this motivates us to study these waves in the ICME, for which we are using the data from the wind spacecraft. And here we are using high cadence data from the instruments on board the wind spacecraft. And we are basically taking the ICME events which are recorded in the wind ICME catalog, which is present on the NASA's website, through which we have taken roughly around 401 ICME events, which we have later on shortlisted, or I would say categorized by running the power spectral density algorithm, through which we shortlisted these events which showed explicit bump in the PSG. Later on, which further narrowed down our events by running the normalized magnetic helicity test to identify the wave polarization and to get the waves, to get the signatures which are similar to your KW waves. And finally, we use the theta wave test to confirm our observation whether that it is exactly a KW wave. So let us see one by one how we proceeded with the observation of KW waves. So this figure is basically an interplanetary parameters plot for plot for an ICME which was observed by the wind spacecraft on 24th of October 2011, where the first panel basically represents the IMF magnetic field along with the fluctuations in the magnetic field delta B, followed by the components of the magnetic field Bx, By, Bz, later on followed by the elevation angle and azimuthal angle theta and 5, plasma number density Np and plasma velocity Vp, followed by the temperature anisotropy ratio, which is ratio of parallel upon perpendicular component of the temperature, and then it is followed by the plasma temperature Tp and plasma beta. So this in this plot, basically the cloud boundaries have been identified or basically identified from the ICME catalog, which is given in this link. So here you can observe this particular region. This particular region where we can see there is a sudden rise in the interplanetary parameters. That is, we can see a rise in the number density. Sorry, no, rise in the magnetic field, its components, even in the number density and solar wind velocity, even in the rise in temperature as well as plasma beta. These signatures, as per previous studies, suggest that the observed region or observed region is basically your ICME shock, which is followed by this blue shaded region where we can see the plasma has become quite turbulent, which suggests that the the observed region or the blue shaded region is an ICME sheath. After the sheath region, this pink shaded region is basically a region where we observe signatures such as large rotation of the magnetic field, IMF magnetic field, as well as smooth rotation of the IMF components, along with a decrement in the number density as well as the velocity, as well as decrement in the temperature and low plasma beta signatures, which suggest that the observed structure is an ICME magnetic cloud. Fine. So in this plot, we can see we have marked a particular region, this yellow shaded region, which will be our area of focus throughout this talk or throughout this study. Basically, our observations suggest that this particular region is nothing but a current sheet. So let us see how we were able to reach this conclusion, whether they are actually current sheet or something else. So for that purpose, let us see this particular plot, which is the expanded version of the interplanetary parameters, where we have the total magnetic field, By, the Y component of the magnetic field, the azimuthal angle 5, number density and temperature Tp. Here the red shaded portion basically represents the region of our interest, and here we can see the IMF magnetic field roughly decreases from around 14 nanotesla to roughly around 9.5, 9.6 nanotesla. And the magnetic field's Y component has a change of its polarity. Along with that, we can observe the phi angle as a sudden transition, sudden transition or sudden rise, fall in the values from say 270 to 50 degrees, as well as the number density and temperature increases. This all signature suggests that this particular region is nothing but a current sheet, which exhibits a reconnection exhaust and is basically spanning roughly around 39 minutes. Now question arises whether this current sheet is actually formed at the trailing edges of the magnetic cloud, or is it something else? For that reason, we use the data from the WSS Enlil simulation, where basically this is a snapshot of the Enlil simulation, where we are basically representing the ICME magnetic clouds as crescent shaped contours, this one, which are moving with varying solar velocity. And this white line is basically your heliospheric current sheet. So here, this snapshot is taken at around 16 hours UTC on this 25th of October 2011, where we observe that at this particular point, basically, there is an interaction between this passing CME and the heliospheric current sheet. And thus, the Enlil simulation suggests that the region of interest is basically nothing but an region wherein ICME has interacted with the heliospheric current sheet, and because of which there is a generation of a reconnection exhaust. And there have been several studies, both numerical as well as observational, which suggest that there near the reconnection exhaust, there have been several means different kinds of MHD as well as kinetic waves can be generated. Thus, this motivates us to choose this region as our region of interest to study the different waves, whether it be MHD or kinetic waves. So for that purpose, first of all, we use the power spectral density method, which basically gives us the power of the signal present. And here basically we have taken the power spectral density of the trace of the magnetic field using the FFT algorithm. And the usually the power spectral density of solar wind has an power law behavior, that is it follows f raised to minus alpha, where the alpha is the spectral index. And based upon the wave scales, the turbulence is divided into three regions. The first region, which is at the lower frequencies, which in which the energy is injected into the uh, wave, and it is called as the injection region, which has a spectral index of roughly around f raised to minus 1, which is then followed by a region called as the inertial range, which has a spectral index of minus 5 by 3. And thus then the inertial range is followed by something called as the dissipative range, which has a spectral index of minus 7 by 3. Uh, the inertial range and the dissipation range are basically marked, or you can say observed by a spectral break. In the sense, there is break between these two different ranges, and we can say ki our wave is making transition from inertial range to the dissipation range. And whenever we have a dissipation range, there is a steep fall in the power spectral density, which suggests that the wave is transferring its energy in the form of dissipation to the surrounding plasma. And another interesting fact about the spectral break is that it basically tells us the difference between the MHD and kinetic modes, or kinetic domains. In the sense, whenever we observe the spectral break, we say ki our wave has made a transition from the MHD scale to the kinetic scale. And from this figure, basically we have fitted the both the region before and after the spectral break, which is roughly around here. Uh, so here the red fitted region basically has a spectral index of f raised to minus 1.66, which is corresponding to the inertial range. Followed by this, we have this green shaded region, which has a spectral index of minus 2.71, which is close to the dissipative, which is basically a dissipative range. And if you observe, I have basically put a shaded region. This shaded region, marked by the vertical dashed line, is nothing but the proton gyrofrequency, which basically I have taken by estimated, or I would say it is range of the gyrofrequency, which I have estimated by taking the minimum and maximum magnetic field within our region of interest. So now, since we have identified that this particular region has some dissipation or has some exchange of wave energy, we move to a very interesting test, which is or interesting test or interesting quantity, which is we call what we call as a magnetic helicity. The magnetic helicity, as I say, it is a very interesting quantity because it tells us about the degree of twistness of the magnetic field lines, and it is actually an topological variant of the MHD equations. That is, it remains in conserved in ideal ideal MHD equation. And mathematically, it is explained. Oh, okay, the image is overlapping it. Let it be. Mathematically, it is given by this expression where HM is equal to integration of A dot B dot dV, where A is your vector potential and B is the magnetic field. And usually in single spacecraft observations, uh, we use a quantity called as the reduced magnetic helicity, where it is given by this particular expression, where this we take the imaginary component of the S23R, which is nothing but a spectral matrix estimated using the correlation function of the magnetic field, for which the diagonal elements basically represents the magnetic energy and the off diagonal elements represents the helicity. Um, and the K1 is basically the wave. So here the Y and Z star basically represent the Y and Z component of the magnetic field. And what we are doing exactly is that we are adding a phase shift of 90 degree to one of the component in order to measure the polarization. Thus, this particular quantity will give us the polarization of the wave. However, recently there has been another quantity called as a normalized magnetic helicity, which has been used by the community in order to get a better sense of polarization, as well as we get a proper idea okay, what is the polarization of the wave. This normalized magnetic helicity is basically given by or represented by quantity called as sigma m, which is if you see the numerator is this reduced magnetic helicity, which is divided by this expression, which is nothing but the total magnetic energy. Then your normalized magnetic helicity, as I say, it is a dimensionless quantity and usually it lies between plus minus 1. So whenever it is greater than 0, or I would say it is equal to plus 1, I would say that my wave is left-handedly polarized. Whereas if it is less than 0, or it is close to minus 1, I would say that my wave is a right-handedly polarized wave. Fine. And suppose if it is equal to 0, then I would say that my wave is a plane polarized. Furthermore, there is another interesting fact about this magnetic helicity. Maybe I can show you the next spectrum and then we can discuss it. Uh, this is a particular plot of our magnetic helicity spectrum, which we have estimated using FFT algorithm, where you can see you can see that the magnetic helicity within the inertial range, which is this, oscillates between positive and negative. So on an average, uh, in the inertial range, the magnetic helicity is close to 0, or we would say it is 0. However, as we move to the dissipative range, which is above the zero point 0.1 hertz, we see that the magnetic helicity makes it transition to the negative direction. Actually, whenever we have the dissipation range, the helicity shows us the direction of polarization of the wave, and here we see it is making a transition to the sigma m value of minus 0.38. So this suggests that the observed wave is right-handedly circularly polarized wave. However, as we saw in the earlier slides, this may be signature of either your quasi-perpendicular KAW waves or your quasi-parallel magnetosonic waves, magnetosonic Whistler waves. So, in order to confirm whether actually we are observing is a KAW wave, not a Whistler wave, we use a technique called as the distribution of sigma m as a function of flow angle theta v, where theta v is nothing but the angle between the solar wind velocity and the magnetic field, where we are estimating the sigma m. The expression remains the same, which was given in the previous slide, using wavelet transformation instead of an FFT transformation. And here we distribute the sigma m as per different look angles. Look angles in the sense we distribute them according to different theta VB values, and depending upon the direction of the, or I would say the angle where we are observing the helicity patch, we conclude that our wave is whether a quasi-parallel wave or a quasi-perpendicular wave or an oblique wave. In the sense, as I was saying earlier, if the waves, if the observed helicity is close to between 0 to 45 degrees, I would say it is a quasi-parallel wave, or between 135 to 180 degree, I would say it is a quasi-parallel, anti-quasi-parallel wave. Or if it lies between 90, say like a plus minus 30 degrees, that is from 60 to 120 degree, I would say my observed wave is a quasi-perpendicular wave, such as a KW wave. And if it lies between the intermediate values, that is from 45, say like a 60 degrees, or from 120 to 135 degree, we say that the observed wave is a oblique. So in this figure, basically we have represented the sigma m as a function of theta vb, and where we observe that there is a strong patch of helicity in the negative direction, which is more showing dominance or dominant signature near 90 degrees. This particular observation suggests that our observed wave in this particular HCS interaction is nothing but your kinetic Alfvén wave, thus confirming or thus giving us the first in situ observation of the KAW waves in the magnetic cloud. And thus, to summarize our result from the PhD spectrum, we observe that there is a quite steepening in the region above the gyrofrequency, which suggests that there is a dissipation of the wave. Moreover, the helicity spectrum shows a distinct negative bound around minus 0.38 near the gyrofrequency, which indicates that the observed wave is a right-handed polarized wave. Furthermore, our theta VB test confirms that our observed wave is nothing but our quasi-perpendicular KW wave. So now, okay, I have convinced you that this is a KW wave and all, but what are the implications? In the sense, we have identified the KW wave in the ICME magnetic cloud. But what is the actual implication of our finding? First of all, as I am saying, or as we know, that our ICME magnetic cloud is a very closed structure. Closed structure in the sense it doesn't interact with the surrounding solar wind. Thus, it doesn't experience any force and it remains in a stable equilibrium. However, there has been some observations conducted by Feng and Wang, where they observed that few magnetic clouds exhibited certain regions, mostly at the center as well as the leading and the trailing edges, were exhibiting high temperatures or regions or pockets of high temperature. This observation was quite confusing because ideally the magnetic clouds, since they are expanding, the temperature should decrease. But here they are observing some high temperatures. So for this purpose, they suggested two methods or two reasons. First one was they suggested that this high temperature in the magnetic clouds may be due to the result of this solar origin. In the sense, these magnetic clouds might be carrying these pockets of high temperature from the point of origin through the corona. And another reason which they proposed was this particular heating effect was due to some internal process. In the sense, they suggested that internal process such as magnetic reconnection or current sheet formation may be leading to this excess heating. And there have been several studies, both numerical and theoretical, numerical and observational, which suggest the presence of presence of the current sheets and magnetic reconnections in the clouds, as well as this study suggests the generation of KAW waves near this reconnection, near this current sheets. Thus, suggesting that the KAW waves might be playing a role or in this excess heating. Furthermore, as we say, we have identified KAWs. So, identification of this KAW wave sheds a very important light on the wave to particle interactions in the magnetic cloud. Till now, as I have already discussed, that the magnetic clouds have been observed as a macroscopic structure. However, the observation of KW waves help us to understand the wave particle interaction, thus enabling us to understand how the heating and cooling will take place because of the KW and ASC waves in the magnetic cloud. Furthermore, the observations also suggest that it creates regions of high temperature as well as high plasma beta inside the cloud, which are not features observed in usual magnetic clouds. Furthermore, in our observation, we found that the presence of the KW waves cause and rise in the parallel component of the temperature. That is, it basically increases the T parallel upon T perpendicular. Or if I follow the standard notation, it decreases the temperature anisotropy of the system. This has far implications. Basically this temperature anisotropy has implications in the sense because of this increase in instability. Increase in the anisotropy, there will be formation of kinetic instabilities, which may further drive the plasma of the ICME cloud towards the equilibrium and thus generating several other wave modes, thus making it very interesting to study this. Furthermore, we believe our study proves to be very crucial for understanding the dissipation mechanisms in the force-free structures such as magnetic cloud. In the sense, if you are able to identify the dissipation process or the dissipation mechanism properly in the clouds, we will be able to understand how they evolve thermodynamic. Thus, uh, this basically tells us that understanding or study of the kinetic waves is very much important in these structures, this large-scale magnetic structure. So now, one question arises: what next? What next in the sense, since there have been several studies which suggest that the Alfvén waves are major contributors to the heating of this plasma. We would like to extend our analysis to identify the heating caused by the Alfvénic fluctuations in large-scale magnetic structures such as your ICMEs or CIRs, and furthermore, see how much their contribution is present for different Alfvénic modes. Along with that, as I said, there is a change in the temperature anisotropy of the system, which causes generation of certain kinetic instabilities. And it is very interesting to study these kinetic instabilities and how they are basically controlling the dynamics of the nearby plasma. And furthermore, we wish to provide a linkage between the waves and instabilities, because waves are basically macroscopic things and instabilities are the kinetic things. So this our aim is to basically link both these phenomena, thus enabling us to study the system such as ICME as a whole in both microscopic as well as microscopic domain. Thus, this I would like to conclude my talk with few slides. This is basically the slide of my paper, which was published recently in APJ, and this is what we are doing at MU. Under the guidance of Dr. Raghav, we are basically studying structures such as ICMEs, CIRs, where we are observing Alfvén waves, then their kinetic versions, or we are even studying the current sheets, as well as we are studying the polytropic index, which is basically for the thermodynamics. We are studying the particle energization processes in ICMEs, as well as we are studying the plasma instabilities, as well along with that we are studying the planar magnetic structures, and uh, along with that we are also even studying the geomagnetic storms and Forbush decrease methods, Forbush decrease processes. So I would like to thank my collaborators, whose valuable insights have been helping us to give this such novel work. And thus, I would like to thank you all for listening me for I don't know how many minutes. And that's it for today.
Yeah, dear all, you can ask questions now to Kishore if you have.
Yes, yes, yes. Maybe I can stop the sharing. Yeah.
Yeah. You can type in the chat box also the question so that I can read and ask to him.
Hi, Kishor.
Hi, Zubair. Yeah.
Yeah, can you go back to your sigma m explanation?
Yes, yes. One second.
Sigma.
I will share my
Wow.
screen. Yeah. Sigma M.
That normalized magnetic helicity. Yeah.
This one.
Yes.
Yeah. Huh.
Um, if I remember, you said like sigma m less than zero correspond to right-handed polarized and greater than zero correspond to left-handed polarized.
Yes.
Uh, uh, but as per the literature, if you go into G-wave analysis and other stuffs, then in most of the cases, this is the reverse situation. Like when your sigma m is greater than zero, it is called right-handed polarized. Less than zero, called left-handed polarization. Okay, so it seems to be different here. Can you please explain me why it is so?
Actually,
Because that is
this,
going to change your definition of the wave itself.
yes, yes, I can agree. Actually, the direction or the direction of the sigma m usually depends upon the orientation of the magnetic sector. In the sense, if it is inward sector, then it will be having the signs which you have suggested. Whereas if it is outward, it will be having this particular sign. So, in order to get a proper orientation, usually we reverse the sign of the magnetic field in order to get the proper orientation. In the sense, this confusion is removed by changing the sign of the magnetic field. What you are saying is correct. In the literature, sometimes we observe that they are showing the opposite. But it depends mostly on the
So,
direction or the orientation of the magnetic sector.
so that means you you make the correction in the sector boundary crossing and then you
Yes.
perform this
Yes, yes. We
analysis.
basically rotate the coordinates and then we estimate this to avoid this
Okay.
confusion.
Okay. Thank you.
There is one question in the chat box from Mr. Kubera Raja. How to find the solar wind speed? If Kubera is there, can you elaborate the question? Because how to find solar wind speed? That means how to find from the particle count you are measuring, or can you explain the question a little bit more? So he asking the question how to find solar wind speed, but so
Maybe he or she is asking regarding the data. Maybe the IP from the IP plots he or she might be asking. Not sure.
you have shown the bulk
Yeah, I have shown
parameter
the IP
panel,
plot.
right? Yeah, in
Yeah.
that. solar wind speed is there.
Yeah, this
Upper
I
density
think
is
I
there.
have taken from the 3DP instrument, which is on board of
Ah,
the Wheel spacecraft. Like that's I think that's the answer for your question. If you can help, shall we
uh,
get shall we find the
yeah,
solar wind speed? Not able to understand the question.
uh,
Okay,
Kubera, can you come to audio? Like question
yeah,
is not clear. That's why.
okay. There is another question of Utkarsh.
Okay. From
During the
Utkarsh.
sir, sir,
Yeah.
during the CME propagation, we are studying solar wind. I don't know how to find the wind speed, sir. Solar
Kishor.
wind.
So can you explain can you tell me the question again, please? I was not able to hear it properly. Can you repeat it again?
Kubera, can you repeat it again? The question.
Yes, sir, yes, sir.
Yeah,
Sir,
yeah.
during the in catalog, and they are providing the initial speed like that, space speed, apparent speed, space speed in IC and color in catalog. But I don't know to calculate the speed during its propagation towards side.
Means I think what I can infer ki here you are asking basically the speed of the ICME, right?
Yes, I see. Yes.
Okay. Okay, this ICME speed is basically we observe from the spacecraft data only. Like here we are observing the different ICMEs which are measured by the instrument present on the wind spacecraft. The speed depends upon I think that's your question, right? Means I'm actually not getting, but I think that is the answer. We are basically measuring the speed to the onboard instruments present on the wing, velocity. Yeah.
Okay, okay, sir.
Okay. Okay. There is another question by Utkarsh.
Why did you use wavelet transform for the theta VB test?
Yeah, yeah, yeah. Basically, the Wheeler transformation. Like first of all, if we consider where is the plot? Yeah, one second. This particular plot of normalized magnetic helicity is basically estimated using FFT, whereas whenever we are using Wheeler transformation, in this particular case, why? Because Wheeler transformation will tell us the okay, wait a second. Okay, there is another question. Whenever we are using Wheeler transformation, basically it will give us the information of the frequency present at different time scales, and thus it will help us to identify the signatures in a proper way, as compared to the standard FFT, where standard FFT, where we basically have this, we don't get information of the time. We directly get the frequencies of the signal present. I think that would be the answer for your question, Utkarsh. Okay, there is another
There
question.
is another question. Why do we say kinetic Alfvén wave? Like, what makes it kinetic?
Okay, so I think I have discussed it. Actually, kinetic in the sense, basically it is, uh, okay, what makes it kinetic? Basically, by the kinetic in the sense, it is a wave which basically interacts with the particles. In the sense, there is a kinetic theory which suggests that if we are treating the plasma as individual particle. Thus, I think that is why we are calling it as kinetic alpha wave. I
Yeah,
think that.
you showed one picture where the
Yeah, yeah, the
particles
one picture
grouped
wherein
together
it
as
is
well as
present.
particles separated out. Can you?
Yeah, 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 one second.
There was a
You are not.
cartoon. Ah, the
Yeah,
same one.
yes,
Yeah,
yes, yes. This is the thing which I was saying. In the MHD waves, you basically follow the collective behavior, fluid-like behavior, whereas in kinetic we have the particle-like behavior. That's why I think we call it as the kinetic Alfvén wave because it is treating the particles in the kinetic domain. Yeah,
yeah, because number density is low, so low in the solar wind, where the situation is like particles are separated out, not
yeah.
with the same temperature. So the kinetic physics is the better one to treat the
Hmm.
scenario there.
Right, right, right.
Then one another question, like how do we find the current sheet from the IP parameter evolution?
Okay,
Maybe
current
in
sheet
your
के लिए means
panel, yeah.
yeah, means I think I have given the criteria
Yeah.
in the sense we observe that the there is a decrement in the magnetic field, as well as usually it is said that one component of the magnetic field has a zero line crossing, in the sense it changes its polarity, just like in this case we are having the change in polarity of the y component of the magnetic field. Also, there is large fluctuation in the elevation and azimuthal angle, not the elevation angle 5, and also we observe that there is rise in the number density as well as temperature. This particular signature suggests that we are observing the current shift. And also, actually, I have not mentioned here, but there is rise in the plasma beta as well. In the sense, if I go to the previous slide, yeah, here you can see that the plasma beta has increased in this particular region. This suggests that the observed region is basically your current sheet. I think Sachit, that addresses your question.
Yeah,
Anyone
there's
else?
a hand from Yogesh.
Yeah,
Yeah, Yogesh.
I may have missed it, but
Yeah.
in what frame reference you have calculated the magnetic helicity?
We are basically using GSC coordinates. So basic GSC coordinates for all the analysis. I think I forgot to
So,
mention it.
but
Yeah,
if you calculate that in the like plasma frame, then the helicity may change.
it may means I have not tried it. It may change. I am not sure about
Yeah,
it actually.
because if
Yeah.
you change the frame of reference, then the it's kind of changing the rotation and other directions.
It might
So
change. Means I have not tried it. Maybe I can try it out. Means I'm not sure what change it will have, but I think it can change as you're suggesting.
mhm. Okay.
Yeah. How can we confirm alpha waves are occurring in ICME type P region?
Yeah.
Ashwin, usually for alpha waves, we find the correlation between the velocity and the magnetic field, through which we can identify whether our alpha waves are outwardly propagating or inwardly propagating. And along with that, there is another quantity which we can estimate called as the Althusser variables, through which we can uh, basically form the normalized cross helicity, which is a parameter which can help us to identify, which is again basically just finding the correlation between V and magnetic field and velocity, which will tell us the presence of alpha waves in the ICMEs. Is it giving the answer to your question, Ashwin?
I think Ashwini is here, right? Yeah, Ashwini is here.
Ashwin, are you there?
Yeah, he replied. He got the.
Okay, yeah, okay, yeah. Um, yeah, you can observe alpha in the inertial region, Utkarsh.
Okay. So, any other questions? I think no more question in the chat box.
Yeah, I think yes.
Let me see whether any hands are there. No.
Don't see anything.
Yeah. Yeah, Kishore, the talk
Yes.
was very interesting. It is very fascinating.
Hmm.
Like, it's good that you are from observations, you are able to detect the kinetic alpha waves in the ICME. So
Yeah.
that's a very interesting observation. And in CIR also, this is there. Like, you're able to
CIR,
see in CIR also.
sir, and as per my knowledge, right now no one has observed it, and
Okay.
maybe in future we can try that. But CIR, obviously, you can get it. It can
Okay.
be
And,
observed.
and also in interacting CMEs, like in multiple CMEs clubbed together, sometimes they pass through, right?
Yeah.
Mostly close to active regions means active time. It will not be isolated CMEs. There will be interacting CMEs. So
Interacting CM.
during
Yeah, yeah. The CM is
during such a
CM.
scenarios, the possibility of alpha wave generation is more, or something, some bias is there. Or could you observe? Or,
Means there have been several observations where they have where we have observed alpha waves in the CME interactions. Yeah, in that case, we can observe these alphanic waves in CME interactions. Usually, I don't remember exactly the articles, but recently we have observed these waves inside the CME interactions.
oh,
And yeah,
okay.
it's basically there have been several observations which suggest we can find these waves between different interactions, such as recently we observed it between the ICME HSS interaction. So CME, there have been several observations.
Okay. So, okay, Kishore, thank you for delivering such a nice talk for Indus. And
Yeah, thank you for giving me the
we appreciate
opportunity.
your effort in doing carry forward this research, and we wish you all the best for further
Thank you.
things. Okay.
Bye.